In this video, we'll be giving a demo of constraints of several types. As a reminder, constraints, also known as integrity constraints, impose restrictions on the allowable states of a database beyond those that are imposed by the schema that's been defined in the types of the attributes. We have a number of different types of constraints. We have non-null constraints, which specify that a particular attribute cannot have null values. We have key constraints that talk about uniqueness in columns or sets of columns. We have attribute-based and tuple-based constraints, which specify restrictions on the values in attributes or the values across attributes in particular tuples. And finally, we have general assertions, which are quite powerful. They allow you to specify constraints across an entire database. As we'll see in the demo, not all of these constraint types are fully implemented. There are some limits on the attribute-based and tuple-based constraints in systems as compared to the SQL standard, and general assertions have not been implemented yet in any database system. But we will give examples of what they would look like had they been implemented. A very important type of constraint is referential integrity or foreign key constraints, and those will be covered in the next video. For a demonstration of constraints, we'll be returning to the same simple college admissions database that we used for our SQL demos. We have 3 tables, one with a few colleges, one with a number of students, and finally a table that has information about students applying to colleges. Let's start by creating a table with a non-null constraint. So non-null is a pretty simple type of constraint. If we decide that our GPA values in our database must not take on a null value, when we create the table, we just add the keywords not null in the declaration with that attribute. Let's run the creation of the table. Let me mention right up front, we're going to be seeing a lot of this word affected, this misspelling here, which gets on my nerves, but I'm not going to mention it again. Okay, so let's do some insertions and updates just to experiment with a not null constraint. We'll start by inserting 3 tuples. The first one has no null values at all. The second one has a null value for the high school size, which should be allowed. And the third one has a null value for the GPA, which should not be allowed. Let's run these 3 insert commands together, and we see, in fact, the first 2 succeeded where the third one generated an error. If we go and look at the table, we'll see that indeed we got our first 2 tuples, including the null for the high school size, but there was no third tuple inserted. Now we'll try a couple of update commands. Both of them are going to set the GPA to null, the first one for the student with ID 123 and the second for the student with ID 456. If we look at our data, we see that we do have a student with ID 123, so when we try to update that GPA to null, we should get an error. But we don't have a student whose ID is 456. So even though we're going to run a command that tries to set GPAs to null, because there's no matching data, no data will attempt to be updated and we won't get an error. Let's run the query, the 2 updates, and we see indeed that the first one caused a constraint violation and the second one did not. Now let's take a look at key constraints. I've dropped the previous version of the student table, and now we will create a new one where we're declaring the student ID to be what's called a primary key. As you may remember, a key constraint specifies that the values in the column that's declared as a key must be unique. So let's go ahead and create the table, and now let's experiment with inserting and updating some data. We'll attempt to insert 3 students. First one, 123 Amy, second, 234 Bob, and third one, 123 Craig. Since the third insert will generate a key violation because there will be 2 copies of 123 in the ID column, that one should generate an error. We run the queries, the inserts, and indeed the first 2 are fine and the third one has a key error. If we go and look at the data itself, we'll see that the first 2 were inserted and the third one wasn't. Now let's take a look at some updates. The first update is very simple. It tries to set Bob's ID to 123. Since Amy already has ID 123, that should generate an error, and when we run the update command, indeed it does. Now we're going to do something a little bit trickier. We're going to run an update command that subtracts 111 from each student ID. Now you might wonder, why did I choose 111? Let's take a look. If we subtract 111 from Bob's ID, 234 will turn into 123 and we'll have a key violation. On the other hand, if the command first updates Amy's student ID to 12, then we won't have a key violation when Bob's is turned into 123. So whether we get a key violation in this case could depend on what order the system chooses to execute the update. So let's just run it and let's see what happens. Well, things look good. We didn't get an error. Let's go look back and refresh the table, and we see indeed that both of the updates succeeded without a violation. So now let's set the student IDs back to what they were by adding 111. Let's run it, see what happens. Whoops! Well, this time we got an error. So we got a constraint violation error, a key violation, and nothing was updated. That's presumably because the system again updated Amy's ID first, and that generated an error with the 123 for Amy. So this sort of demonstrates that when it can be pretty tricky when key violations or other types of constraint violations are detected and when they aren't. Now, we did mention earlier that there's a notion of deferred constraint checking. So if an application has knowledge that it would rather have constraints checked after a bunch of changes rather than in the middle, deferred constraint checking can be used for that purpose. In this demo, we're doing immediate constraint checking. You might have noticed in the previous example that I used the term primary key when I declared the student ID as a key. In the SQL standard and in every database system, only one primary key is allowed per table. That's why it's called primary. And often the table will be organized based on that key, making it efficient to do lookups for values for that particular key. So if we decided we wanted to declare two primary keys in our table, the student ID and the student name, we would get an error. Now, that's not to say we're not allowed to have multiple keys in a table. In fact, we can have as many as we want. Only one of them can be declared as primary, but we can declare any number of attributes or sets of attributes to be unique. And that's, again, declaring a key constraint. It says we can only have one, that we must have unique values in that column. So let's create our table with the student name now also a key, along with the student ID. And we'll do a few updates just to check that. So we'll attempt to insert 5 students. 1, 2, 3 Amy, 2, 3, 4 Bob. So far, so good. When we try 3, 4, 5 Amy, we should get an error because we've now declared that the name must be a key as well as the student ID, so we won't be allowed to have 2 Amy's. 4, 5, 6 Doris should be good. 5, 6, 7 Amy should again generate an error. We run the query, and indeed, we get 2 errors. So far, we've seen only keys that are one attribute, but as you know, we can have keys that span several attributes. That's not to say that each attribute is a key individually, but rather the combination of values for all of the attributes must be unique in each tuple. So let's suppose that our college name is not unique on its own, but college name and state together are expected to be unique. Now, syntactically, we can't put the primary key statement with the attribute anymore because it involves multiple attributes. So the syntax is to list the attributes first in the create table command, then use the keywords primary key and put the list of attributes constituting the key in parentheses. So let's create the table. Now let's insert some data. I tried to pick a college name that's kind of generic, Mason. I don't know if I succeeded, but we'll try to insert a Mason College in California, a Mason College in New York. Those should succeed because the 2 columns together need to be unique, but not the individual columns. And then we should get an error when we try to generate a 3rd tuple with Mason, California. We run the query, we run the inserts, and indeed we do. Now let's use multi-attribute keys to declare some interesting constraints. We're going to create our apply table, and we're going to have 2 key constraints. The first one says that the combination of student ID and college name must be unique in each tuple. What that's really saying is that each student can apply to each college only one time. We're also going to say that the combination of student ID and major must be unique in each tuple. That means that each student can apply to each major only once. Now, a student can still apply to several colleges and several majors, but only one time for each. So let's create the table, and then let's try inserting some data. We'll insert quite a number of tuples, and let's take a look at what we expect to happen. Our first tuple says 1, 2, 3 applies to Stanford and CS, and then 1, 2, 3 also applies to Berkeley and EE, no problem. 1, 2, 3 tries to apply again to Stanford, and that should be error because that's the second instance of the combination of 1, 2, 3 Stanford. On the other hand, 2, 3, 4 should be able to apply to Stanford. 1, 2, 3 comes back and wants to go to MIT, but tries once again to major in EE. That should generate an error because the combination of 1, 2, 3 and EE already appears in our second tuple. And finally, 1, 2, 3 applies to MIT, but in biology, and that should work just fine. So we'll run the query, and we'll find indeed the first 2 tuples, and the 4th and the 6th were fine, but the 3rd tuple generated an error because of the second application to Stanford, and the 5th because of the second application to EE. Let's go take a look at the data. And here we see in the apply relation that we did indeed insert the 4 tuples, but not the 2 tuples that generated the key error. Now we'll try a sneaky update command. We'll try to take our 4th tuple and we'll identify it by having the college name be equal to MIT, and we'll try to be sneaky and change the biology major to CS. That will then violate the constraint of the uniqueness of 123 CS, so if all goes well, that update will be disallowed. Here's the update command, setting the major to CS where the college name is MIT. We run the command, and indeed, it generates an error. The last thing we'll show in this example is how null values work with keys. So we'll try to insert 2 tuples, again using 1, 2, 3, where both the college name and the major are null. So as a reminder, the first and second attributes need to be unique, and the first and third attributes need to be unique. So if nulls count for keys, then it will generate an error. What we'll see is that we actually don't get an error, and we in fact do have the data inserted into the table with the null values. So the SQL standard and most database systems do allow repeated null values even in columns that are declared as unique. For primary key declared columns, most systems, although not all, do not permit repeated null values in them. That completes our demonstration of key constraints. Now let's look at attribute-based check constraints. Let's create our table again for students, and this time we'll add 2 constraints to 2 of the attributes. For the GPA, we're going to add the keyword check and a condition, looks kind of like the where clause in a SQL query. This condition specifies that GPAs must be less than or equal to 4.0 and greater than 0. We'll also put a check constraint on the high school size, saying that the size of the high school must be less than 5,000. So these are examples of sort of sanity checks that are mostly used for catching data entry errors, saying that the attribute values must be within the expected range. Let's create the table, and now we'll take a look at some data. This time we'll just insert 2 tuples. It'll be pretty easy to see how these constraints work. The first one inserts Amy with a reasonable GPA and a reasonable high school size. The second one inserts Bob with a reasonable high school size, but his GPA looks a little out of whack. We run the query, and the first row is inserted, but the second one isn't. We take a look at the data, and we see that just Amy has been inserted. Now to test the constraint on the size of high school, we'll try to run an update command that multiplies all high school sizes by 6. Here's the command, and when we run it, we get an error. So attribute-based constraints allow us to associate a condition with a specific attribute, and that condition is checked whenever we insert a tuple or update a tuple to make sure that all of the values in that attribute satisfy the constraint. A slightly more general notion is tuple-based constraints. Tuple-based constraints are also checked whenever a tuple is inserted or updated, but they're allowed to talk about relationships between different values in each tuple. And because we don't associate them with a specific attribute, the check itself is put at the end of the declaration of the table. So we start by declaring all the attributes, and then afterwards we put the keyword check again, and then the condition inside parentheses. Now this condition may look at first a little bit odd to you. It says that for each apply tuple, either the decision is no, or the college name is not Stanford, or the major is not CS. Why don't you think about that for a second and think about what it might be saying. Now, if you're good at Boolean logic, you might have written this down using logical expressions and used some of De Morgan's laws and turned your ors and nots into implications. If not, I'll just tell you that what this is saying is that there are no people who have applied to Stanford and been admitted to CS at Stanford. Specifically, either they haven't been admitted, or the college is not Stanford, or the major is not CS. We'll create the table, and then we'll experiment with some data. First, we'll try to insert 3 tuples. The first one has a student applying to Stanford CS but not being admitted. Second, they apply to CS, but it's at MIT, and they are admitted. And then finally, we'll generate a constraint violation by having the student apply to Stanford CS and be admitted. We run the query, and as expected, the first 2 tuples are inserted, and the third generates a violation. Now let's try some update statements. So we have a student who applied to Stanford CS and was not admitted, and we have a student who applied to MIT CS and was admitted. So first we'll try to take that Stanford student and change the decision to yes. That's not going to work. So then we'll try taking the student's admission to MIT and converting that to be an admission to Stanford, and that shouldn't work either. We try both of those, and neither of them succeed. In both cases, our tuple-based constraint was checked, and the check condition was violated. Before I do my last set of examples, I did want to explain one thing in case you're trying these constraints at home. The constraints that I've shown so far work perfectly well in SQLite and in Postgres. In MySQL, as of the time of this video, the check constraints, both the attribute-based and tuple-based check constraints, are accepted syntactically by the MySQL system, but they're not enforced. So it can be a bit deceptive because you may create the tables exactly as I've done in MySQL, but then you'll be allowed to insert and update data and violate the constraints. So again, I recommend for trying check constraints, for now, SQLite or Postgres. If you've been a shrewd observer of what we've done so far, it might have occurred to you that we have some redundancy. Specifically, the attribute-based check constraints that we showed can be used to enforce some other types of constraints. Very specifically, if we want to have a not null constraint, we can just write not null. That's a built-in type of constraint. But that's equivalent to adding an attribute-based check constraint that for the GPA, for example, checks that the GPA is not null. As a reminder, is not null is a keyword in the SQL language. Let's create this table, and let's try to insert a tuple with a null value. We have student Amy again with a null GPA, and that generates an error. A little more challenging and interesting is to try to implement key constraints using attribute-based check constraints. So here's an attempt at doing so. Let's just consider a very simple table. We'll call it T, and it will have one attribute A, and we'll try to write a check constraint that specifies that A is a key for T. So here's my attempt at doing so. I declare the attribute, and then in my check, I say that the value of A is not in select A from T. In other words, the value that we're, say, attempting to insert or update is unique in table T. Well, first I'm going to tell you that I'm not allowed to execute that. There's various reasons that I can't execute it. One simple one is that I'm trying to declare a table T and refer to it before it's been declared. Another issue with declaring it is the subquery in the check constraint. We'll talk about that in a moment. There's actually a third problem with this constraint, which is we need to think about when it's being checked. If we say first attempt to insert the value A and then check the constraint, then the constraint would be violated based on the existence of itself. So this is clearly not going to work. There is, in fact, a different expression that might work if it weren't for a couple of other obstacles. Here's an expression that doesn't have the problem of whether we check it before or after we insert A. This is an expression of a key constraint in a way you might not have thought of. What this says is that the number of distinct values for an attribute A must be equal to the number of tuples in the table. In other words, every tuple has a distinct value for A. Now, there was one small issue here, which is null values, because as we mentioned, unique key constraints allow multiple instances of null. But if we don't worry about nulls, then this expression really is a different way of saying that A is a key. We run the query and it doesn't allow it. Again, we have the same problem that we're referring to table T within the check constraint that we're putting in the definition of table T. By the way, that can be overcome. Some systems do allow constraints to be declared or added to tables after the table has been specified. So that would go away. But no systems that I know of allow subqueries, and especially not aggregation within check constraints. Let's pursue a little further the question of subqueries and check constraints. The key example is a little bit contrived because, of course, we can declare key constraints directly. But in some cases, there are very natural constraints that we might want to express with check constraints using subqueries. And I've set up a situation right here. We create our student table as usual, but when we create our apply table, we want to have a constraint that says that any student ID that appears in the apply table is a valid student. In other words, there is a student tuple with that student ID. Now, we can write that as a check constraint. This is syntactically valid in the SQL standard. We specify that the student ID here in the apply table is in the set of student IDs in the student table, but currently no SQL system actually supports subqueries and check constraints. Now, for this specific type of constraint, it happens to fall into a class that's known as referential integrity, where we say that this student ID is referencing a student in the other is referencing the student ID in the student table, and therefore any student ID in apply must also exist in student. And in another video, we'll talk about referential integrity in some detail. But not every check constraint with a subquery falls in the class of referential integrity constraints. The example I gave for keys doesn't, and neither does the one here. Now, this is admittedly a little contrived, but what this says is that every college's enrollment must be bigger than any high school. And so we write that by writing the check constraint in the college table that the enrollment is greater than the maximum high school size from the student table. Now again, no system currently will support this. However, it is in the SQL standard. Now, one thing I want to mention about check constraints with subqueries is that they can be kind of deceptive. And we can take a look at the apply table again. Supposing this was in fact supported by a system, it would check whenever we inserted a tuple into apply or updated a student ID in apply that the constraint holds. But what it will not check is when things change in student. So we could write this constraint, and every time we do an insert or update in apply, it could be verified, but somebody could go and change the student table and delete a student ID, and then what we feel is the constraint here is no longer actually holding. So it can be tricky to use those subqueries. Again, when we do referential integrity, as in this example, the referential integrity system will take care of making sure the constraint holds. But when we have an example like the one with the enrollments, if we say change the high school size in the student table, it would not activate this constraint checking that's specified with the college table. The last type of constraint I'm going to show are general assertions. General assertions are very powerful, and they are in the SQL standard, but unfortunately they currently are not supported by any database system. The first assertion I'm going to write is coming back to the issue of trying to declare or trying to enforce a key constraint without using the built-in facilities. Let me just write the command here. It says we're going to create an assertion called key. Notice that this assertion is not associated with a specific table. Although this assertion only talks about table T, assertions can refer to any number of tables in the database. The way an assertion works is we create an assertion and we give it a name, and the reason for that is so we can delete it later if we wish. Then the keyword check appears, and then we write a condition, and the condition can be quite complicated. The assertion is saying that this condition, written in the SQL-like language, must always be true on the database. So the particular condition that I've put in this first example is the condition we use to check whether attribute A is a key in table T. It says that the number of distinct values in attribute A must be equal to the number of tuples in T. Now, I can try to run this, but I guarantee you that it's not supported. Let's look at some other example assertions we might write if they were supported. Here's an example that implements this referential integrity that I was describing earlier. This referential integrity constraint is saying that the student IDs in the apply table must also exist in the student table. Now, when we write an assertion of that form, we tend to often write it in the negative form. Specifically, we say that it's not the case that something bad happens. It's not the case that there's some tuple in apply where the student ID is not in the student table. You can try on your own to write this in a more positive fashion, but you'll actually find that using SQL constructs, it's not possible. It's actually very common for assertions to specify the bad thing in a subquery and then write not exists. As a final example, let's suppose that we require that the average GPA of students who are accepted to college is greater than 3.0. We can write that as an assertion, pretty much exactly as I just described it. We take the average GPA of students where their ID is among the IDs in the apply relation where the decision was yes, and our assertion states that that average must be greater than 3.0. So far I've described how assertions are created. Let me just briefly mention how they are checked or how they would be checked if they were implemented. Any system that implements this very general form of assertion must determine every possible change to the database that could violate this assertion. In this case, modifying a GPA, modifying a student ID, inserting or deleting from students or apply could all potentially violate the constraint. And in that case, after each of those types of modifications to the database, the system would need to check the constraint, make sure that it's still satisfied, and if not, generate an error and disallow the database change. So I've only talked about creating assertions. Let me just talk very briefly about how a system would enforce general assertions of this form if it supported them. What the system needs to do is monitor every possible change to the database that could cause the assertion to become violated. So if we take a look at this particular assertion, it could become violated if we changed student GPA, if we inserted a student, even if we deleted a student, or if we inserted an application that was now having a decision of yes or updated the application status. So all of those changes have to be monitored by the system. The constraint has to be checked after the change, and if the constraint is no longer satisfied, an error is generated and the change is undone. That concludes our discussion of constraints, with the exception of referential integrity, which is covered in a separate video, and the related topic of triggers, which is also covered in a separate video.